All right, let's kick things off. Welcome to our deep dive, and this time we're going subatomic. We're taking a closer look at tetraquarks, based on some pretty cool research you sent our way. Ever heard of a particle made of four quarks?
Not your everyday particles, that's for sure.
Nope, definitely not. They really push the boundaries of what we know about the universe. You ready to get into it?
Absolutely, always ready to explore the weird and wonderful world of particle physics. Tetraquarks are a pretty hot topic these days.
They really are. And for anyone who needs a little refresher, tetraquarks are these exotic particles that were first theorized way back in the 1960s. But it took us until the 21st century to actually find evidence of them.
Yeah, that's right. It wasn't until 2003 that the Belle experiment detected this particle called the X3872. That was a huge deal. I mean, before that, we were pretty comfortable with quarks coming in groups of two or three, your mesons and baryons, the particles that make up most of the matter we see around us.
Right, the basic building blocks.
Exactly. But then along comes this particle with four quarks. That definitely threw a wrench into things.
It's like finding a new type of atom.
It really is a totally new way to build matter. And the thing is, we're not talking about just one type of tetraquark. There's a whole family of them.
Yeah, double charm tetraquarks with two charm quarks, double beauty tetraquarks with two bottom quarks.
Oh, and let's not forget the all-charm tetraquark, the X6900, discovered just a few years ago in 2020. That one blew my mind.
Four charm quarks, all in one particle.
It was a major discovery. And you know what's really exciting? The existence and the properties of these tetraquarks, especially the X6900, they're telling us so much about the strong force, the force that holds quarks together.
So these exotic particles are giving us a window into one of the fundamental forces of the universe. That's pretty wild.
Exactly. They're really pushing our understanding of how the strong force works, especially at those incredibly tiny distances within the tetraquark.
So we've got all these different types of tetraquarks, and they're making us rethink what we know about the strong force. It's no wonder physicists are so excited about this. Can we get a bit more into the weeds here? Like, what are the limitations of the current models we have for the strong force, and how can tetraquarks help us fix them?
Well, you see, our current models do a pretty good job of explaining how quarks interact at, normal distances like we find inside protons and neutrons.
Okay, so the everyday stuff.
Right. But when you cram quarks really close together, like they are inside a tetraquark, things get a little fuzzy. We're not 100% sure how the strong force behaves in such extreme conditions.
So tetraquarks are kind of like stress tests for our theories.
Exactly. They're pushing us to look beyond our current understanding and to develop new, more complete models.
It's fascinating. Like, we're getting a glimpse of the strong force in action at a level we've never been able to see before. But I bet it's not easy studying these particles.
Oh, you're absolutely right. Tetraquarks are incredibly difficult to study. They decay almost instantly, so you can't just observe them directly.
So how do scientists even begin to study something that disappears so quickly?
It's all about the clues they leave behind, their decay products. We use these massive detectors, like the ones at the Large Hadron Collider. They can pick up the tiny traces of those particles that the tetraquark decays into.
It's like a cosmic puzzle.
Exactly. We have to piece together the properties of those decay products and try to reconstruct the original tetraquark, like forensic science, but on a subatomic scale.
Wow, that's some seriously impressive detective work. And the LHC plays a big role in all of this.
Absolutely. By smashing protons together at almost the speed of light, it creates a whole shower of new particles, and some of those are tetraquarks.
So it's like recreating the conditions of the early universe just to see what pops out.
Mhm.
And then using those super sensitive detectors to sift through the data.
Exactly. It's like searching for a needle in a haystack, but the needle is a particle that existed for a fraction of a second, billions of years ago.
Incredible. It's amazing to think about the level of precision and ingenuity required for this kind of research.
And the collaboration, too. Thousands of scientists all over the world work together on these projects. It's a truly global effort.
Okay, so we've got these tetraquarks. They're more diverse than we initially thought, and they're helping us understand the strong force in new and unexpected ways. It's a lot to wrap our heads around.
Oh, we're just scratching the surface here. Tetraquarks have the potential to unlock some even bigger mysteries of the universe, like the nature of dark matter and the conditions of the very early universe. But that's a story for another part of our deep dive.
We'll definitely have to explore that next time.
All right, welcome back to our deep dive into the world of tetraquarks. Last time we were talking about how these particles are changing the way we think about the strong force. But there's so much more to this story.
Oh, yeah. You mentioned that they could hold clues to some even bigger mysteries, like dark matter and the early universe. I'm definitely ready to dive deeper into that. Where should we start?
Well, let's go back to the very beginning, to the early universe, just fractions of a second after the Big Bang. Imagine a universe that's incredibly hot, incredibly dense, a sea of fundamental particles, including quarks.
Okay, I'm picturing a cosmic soup of particles, a very hot soup.
Yeah, a very, very hot soup. And in this soup, you've got all these quarks just bouncing around. Now, we know that tetraquarks are pretty rare in the universe today, but in those extreme conditions of the early universe, they might have been much more common.
So you're saying that these four quark particles, these tetraquarks, could have been a regular part of the early universe.
Exactly. And that has some pretty big implications for how the universe evolved. Think about it. As the universe cooled down and expanded, quarks started to combine. That's how we got protons and neutrons, the building blocks of atoms.
Right, the stuff that makes up everything we see around us.
Exactly. But if tetraquarks were more common back then, they could have played a role in that process. They might have even influenced the types of particles that formed.
So these exotic particles could have shaped the very structure of the universe as we know it.
It's definitely a possibility. By studying tetraquarks, we're getting a glimpse into the conditions of the early universe. It's like looking back in time to those very first moments after the Big Bang.
It's mind-blowing to think that these tiny particles could hold such profound secrets about the universe's history.
And that's not all. Remember I mentioned dark matter?
Oh yeah, the invisible stuff that makes up a huge chunk of the universe. What do tetraquarks have to do with that?
Well, some physicists think that certain types of tetraquarks, especially those that are really stable and don't interact much with normal matter, could actually be dark matter particles.
Wait, are you saying tetraquarks could be the mysterious dark matter we've been searching for all this time?
It's an idea, but it's still very early days.
Yeah.
We need to do a lot more research. We need to find more tetraquarks, study their properties really carefully, see if they fit the bill.
So we don't know for sure yet, but it's an exciting possibility. What kind of research needs to happen to figure this out?
Well, we need to measure things like their masses, their lifetimes, how they decay, how they interact with other particles. Basically, we need to get to know them a lot better.
So back to the LHC and those amazing detectors.
Exactly. And we also need better theoretical models to help us make sense of the data.
It sounds like we're just starting to unlock the secrets of tetraquarks. Even if they turn out not to be dark matter, what else can we learn from them?
Even if they're not dark matter, they're still telling us something really important about the strong force. They're challenging our assumptions and forcing us to come up with new ideas.
So they're pushing the boundaries of physics.
Absolutely. They're helping us refine our understanding of the very building blocks of the universe. And who knows, maybe they'll even lead to some practical applications down the line.
Okay, now you've got me really intrigued. Practical applications. Like what?
Well, imagine if we could harness the power of the strong force. We could have new energy sources, new materials with incredible strength.
It sounds like something out of Star Trek.
It does, doesn't it? But it's not impossible. The more we learn about the fundamental forces of nature, the more possibilities open up.
It's amazing to think that something as seemingly abstract as particle physics could have such far-reaching consequences.
It really shows the power of basic research, doesn't it? Exploring the unknown can lead to amazing discoveries.
Okay, so we've established that tetraquarks are super important for understanding the universe. But how about we get into some specifics? What are some of the most recent discoveries that are really pushing this field forward?
Oh, there's been a lot of exciting progress lately. For example, the LHCb collaboration at CERN, they found several new types of tetraquarks.
Like what? What kind of new tetraquarks are we talking about?
Well, one of them has a charm quark and a charm antiquark, along with an up quark and a down antiquark, a totally new combination that we've never seen before.
It's like finding a new species of particle.
Yeah, exactly. And they've also found tetraquarks with two charm quarks and two strange antiquarks, and even one with a charm quark, a bottom antiquark, and two light quarks. The variety is just incredible.
Wow, so the tetraquark family is getting bigger all the time. With all these new discoveries, are we starting to see any patterns, any hints of a bigger picture emerging?
We are. It seems like many of these newly discovered tetraquarks are very tightly bound together, which suggests that the strong force might be even stronger than we thought, at least in those close quarter situations.
So tetraquarks are not just these weird exotic particles, they're actually telling us something fundamental about the forces that govern the universe.
Exactly, and there's still so much we don't know. How do they form? Why are some more stable than others? What role do they play in the evolution of the universe? It's a wide open field with so much potential for new discoveries.
It sounds like we're just at the beginning of our journey into the world of tetraquarks. I'm really excited to see what the future holds for this field. Welcome back to our deep dive. We've covered a lot of ground exploring these fascinating tetraquarks, but now I'm really curious about the how. How do scientists actually study these particles? I mean, we can't exactly put them under a microscope, right?
No, not quite. They're way too small and they don't stick around very long.
That's right, they decay super fast. So how do you study something that basically disappears as soon as it appears? It seems impossible.
It's a challenge, that's for sure, but physicists are pretty clever. They've figured out ways to study these elusive particles by looking at what they leave behind. We call those decay products.
Okay, so instead of studying the tetraquark itself, you study the pieces it breaks down into.
Precisely. When a tetraquark decays, it transforms into other, more stable particles. And by carefully studying those particles, measuring their energies, their paths, we can work backwards and reconstruct the original tetraquark.
So it's like solving a puzzle.
Exactly. It's a cosmic forensic investigation. But to do this, we need some pretty amazing tools, like the detectors at the Large Hadron Collider.
Ah, the LHC. It's incredible to think about what goes on there, smashing protons together at nearly the speed of light.
It's pretty mind-blowing. And from those collisions, a whole shower of particles is created, including, you guessed it, tetraquarks.
So it's like recreating the conditions of the early universe just for a tiny fraction of a second.
Exactly. And then those incredibly sensitive detectors capture the traces of all these particles, allowing us to sift through the data and find the evidence for those tetraquarks.
I bet it takes a lot of expertise to analyze all that data.
Oh, absolutely. It's a massive task, requiring not only cutting-edge technology, but also a lot of brain power.
Thousands of scientists from around the world, right?
Exactly. It's a huge collaborative effort. Scientists working together, analyzing data, comparing results, and slowly building a better understanding of these fascinating particles.
It really highlights the global nature of science, doesn't it?
It does. And it shows how much we can achieve when we work together towards a common goal.
Okay, so we've talked about the what and the how of tetraquarks. We've learned about their properties, how they're discovered, and their potential to unlock some big mysteries about the universe.
Mysteries like the nature of dark matter or the conditions of the early universe. It's an exciting time to be studying particle physics.
It really is. And who knows what other surprises are waiting to be discovered. Maybe tetraquarks will lead to new technologies, new energy sources, or even a better understanding of the fundamental laws of physics.
The possibilities are endless.
Well, this has been an incredible journey into the world of tetraquarks. A huge thanks to you for sharing your expertise and for helping us understand these fascinating particles. And to everyone listening, we hope you enjoyed this deep dive into the heart of matter. Keep those questions coming and never stop exploring the wonders of the universe.